it might be worth just describing very, very briefly what a black hole looks like. So, a black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. And if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape the gravitational pull of a black hole. But another description of the event horizon, which confused people all the way through the history of black hole research actually, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. Now that's a direct prediction of Einstein's theory of relativity from the external perspective. There is a central problem though, which is still not solved, which is what lies at the centre of a black hole. You might think of it as an infinitely dense point to which this massive star collapses. So what are we picturing? It's this thing called a singularity. Actually, it's not right to talk about the centre of a black hole, really. Just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that space and time are so distorted that in some sense their roles swap. The singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. But the nature of that thing was not, and is still not, understood. There's a beautiful model, which is my favourite model. It's called the river model of a black hole. You can write the equations as the space being like a river that flows into this thing, almost like a sinkhole or something in space. And the river of space flows at the speed of light inwards on the horizon, and then faster than light inside. When you draw a map of space and time, what you see really clearly is that this singularity thing is not a place in space, it's a moment in time. And it's in fact the end of time in Einstein's theory. So a way that I often kind of picture it or explain it to myself is that space and time have become so distorted that when you look at it from the outside, they flip roles. So space has become time and time has become space. So what you thought of as an infinitely end place in space to which the star collapsed has become a moment in time. And a way to think about why you have to go to it then, it's really beautiful because you think it becomes something that's in the future for anyone or anything that crosses the horizon. Mm-hmm. It's in the future. So it's like if you say, well, I want to escape this thing, it's like saying, I want to escape tomorrow. If I said to you, let's run away from tomorrow, you go, I can't run away from tomorrow, it's in the future. That's what this thing behaves like, singularity. So that's the Einsteinian description of a black hole. What Stephen Hawking showed in a landmark couple of papers is that if you consider quantum theory, quantum mechanics, in the vicinity of the horizon of a black hole, then you find that they glow. They produce particles. They have a temperature. This thing that we've pictured in Einstein's theory as pure geometry, just distorted space and time, actually emits particles. It's called Hawking radiation. And Stephen, in his 1974 paper, gives this hand-wavy description, which is kind of a nice way to picture what's happening. The idea is to zoom in the vicinity of the event horizon of a black hole. You can picture what's happening as a series of particles coming in and out of existence all the time, so-called entangled particles. And so one of those pairs of particles is on the inside of the event horizon and one is on the outside. And then it can happen that the one on the outside, instead of merging back with its partner again, can escape into the universe, removing energy from the black hole as it goes, therefore it's shrinking, which means that one day it will be gone. So black holes are not eternal prisons, they have a lifetime. One day, whatever's in there is returned to the universe. The question was, the central question that was immediately raised by those calculations is this: what happened to all the stuff that fell in? The way I've described it, the way Einstein's theory describes it, is somehow that stuff goes to the singularity, whatever that thing is, the end of time, the region of space-time that's so convoluted and distorted that we don't understand how to describe it at all. But then, one day, the whole thing is gone. All that's left in the far, far future is Hawking radiation, those particles that were produced in the vicinity of the event horizon. The question is it possible, if you could collect all that radiation, all the Hawking radiation through the whole life of the black hole, is it somehow possible, in principle, that the information about everything that fell into the black hole throughout its history is imprinted in that radiation in the far future? Is that true, or is it not true? You might say, why did I ask that question? Seems like a bit of a random question. It's a very important question. Information is conserved in the universe as far as we know. So every law of nature that we have says that information is conserved. So let's say that I take a book and I set fire to it, I incinerate it, I destroy it in any way that I can. In basic fundamental physics, then it turns out that if you could collect every piece of that thing that I detonated or incinerated, every quantum of radiation, every photon, every particle, everything, in principle, if I could just collect it all, then I could reconstruct the thing that I had destroyed. The problem was black holes, quantum mechanics, general relativity. When you put them together, you have this apparent prediction that these things erase information from the universe. This became known as the black hole information paradox. If you crush the Earth down and make it denser, then you get closer and closer to all this mass. And so the gravitational pull at the surface gets bigger. And it's called the Schwarzschild radius of the Earth. And that's, for the Earth, it's about, if I remember rightly, about 1.4 millimeters. For the Sun, it's 3 kilometers. So if you squash the Sun down into a ball that was 3 kilometers, then you'd have to, even light couldn't escape from the surface. And that collapse is what makes a black hole. So it's when something collapses and collapses and collapses, nothing can stop it, and it goes inside its Schwarzschild radius. So the idea, by the way, the Einstein-Rosen bridge, wormhole, that comes from a paper in the mid-1930s from Einstein and Rosen, and it's a property of the space-time, which a man called Karl Schwarzschild discovered actually way back in 1916. And it's if you have an eternal black hole, an eternal universe, so a black hole that's always existed, then you have this mathematical solution, which is a black hole and a white hole and a wormhole connecting them. It turns out you can't go through it because of the way the wormhole evolves as you fall in. But you can imagine those geometries, those so-called wormhole geometries in relativity. Now you need, in order to construct stable ones that you could travel through, you need forms of energy or matter that we don't think exist in the universe. So you can read this. It's a great book actually from a long time ago by Kip Thorne on this called, I think it's called Black Holes, Time Warps and Time Machines or something like that. I can't remember. It's a great book by Kip. And in there you'll see a discussion. And so the guess, it's not been proved, right, beyond doubt, but the guess is that nature will not produce stable wormholes that you can travel through as an astronaut or with a spaceship or so on. So that's where we are at the moment. There are good reasons for thinking that whilst they can exist theoretically, then stable ones that you could go through will not exist. But it's not been proved conclusively from first principles. I should say that there are different kinds of wormholes. So in the study of black holes at the moment, the really cutting edge study of black holes, there is some kind of suggestion that a sort of wormhole might be present and might play a role in solving something called the black hole information paradox.